In the previous video, we have discussed the complex field and introduced the complex numbers, right? Complex numbers are ordered pairs of the form AB, okay, with A and B real numbers. And we can also write them in the traditional form as A plus BI, okay? So here AB are real numbers. Okay, so here there are a few things. So let's call this is the number Z, okay? So let's see some things that we can do with these complex numbers. So one thing, we can define the conjugate. Okay, the conjugate of a number Z, and we write Z bar is A minus B or A minus BI. Okay, just changing the sign of the imaginary part. Now, speaking of that, the real part and imaginary part, well, this is self-explanatory, right? So A is the real part of Z, okay? And B is the imaginary part of Z. But these come up so much in the computations that we write re Z or im Z. Now, some properties. So let's say ZW are complex numbers. So then we have that the conjugate of the sum is the sum of the conjugates. For a product, same thing. The conjugate of a product is the product of the conjugates. Now, there is a cool way of computing the real part and the imaginary part, which is just adding together the number and the conjugate. This way we get twice the real part of Z. And if we subtract, we get 2i, the imaginary part of Z. Okay, and then the last one, when we multiply Z times the conjugate, its conjugate, this is always real and positive. Okay, maybe except when the number is 0, of course. Okay, so these are some properties. I leave these ones for you to check. Okay, the only one I will check is property D. Okay, here if we have D that is AB, then C times the conjugate is AB times A minus B. Okay, and when we do this product, we get A squared plus B squared. Okay, so this is the reason why we are saying that this is bigger or equal than 0, and this is equal to 0 only if A and B are both 0, okay, which is what we were saying, that Z needs to be 0. Okay, this is actually a very important quantity. This is called the absolute value. Okay, so we call the absolute value of Z, we define it as the square root of the product of Z times the conjugate. Sometimes this is called the module of the complex number Z. Okay, both things are correct. All right, so this quantity comes up a lot in the problems and in the computations with complex numbers. Okay. There is one thing here that I would like to emphasize. If we have a real number, okay, in that case, the absolute value is also the square root of the square. Okay, this may sound silly, but if you notice, this verifies the definition of absolute value, which is leave the number as it is if the number is non-negative, and flip the sign if the number is negative. Okay. There are a few more properties that we need to know concerning the absolute value. Okay, let's, as before, take ZW to complex numbers. Then we have that the absolute value is bigger than 0. Well, it's a positive number, the absolute value, unless Z equals 0. Okay, notice that the absolute value of 0 is 0. So this is very important. Sometimes this comes up in proofs where we say, well, we are able to find out that the absolute value of something is 0, and then we know, oh, so whatever this number was in the end, it's 0. And that can be helpful, for example, if you want to show that some complicated expression actually it's equal to 0, or you want to show an identity. Okay. And something else, the absolute value of the conjugate is equal to the absolute value of the number. The absolute value behaves well with the product. Behaves well means that the absolute value of the product is the product of the absolute values. And then a couple funny ones. So the absolute value of the real part is less or equal than the absolute value of Z. And then the last one is the triangular inequality. The triangle inequality that says that the absolute value of the sum is less or equal than the sum of the absolute values. This is the triangle inequality, and it's super important. Okay, this is one of the cornerstone inequalities. We use this one whenever there is an absolute value. Chances are you are going to end up using this. Okay. We have seen this one before. Well, let me not get ahead of myself. All right, so most of these statements are very easy to prove. Actually, statement A, we have already checked. The proof would be here. Okay. We know already that the absolute value is a square root of a squared plus b squared, so nothing to check there. B and BI for only for you to check. Okay. And let's discuss C, D, and E. So proof of C, sorry. Usually when you have the modulus, the absolute value of a complex number, it's more convenient to look into the square. Okay. And this is because then you can use that property, right? You can use the property that the square of the absolute value is the product of the number times the conjugate. Okay, once you can also do the computation directly, and what you get is AC minus BD squared plus AD plus BC squared. Okay, and this turns out to be A squared plus B squared times C squared plus D squared, which is Z squared times W squared. Okay, another option here to prove this, if you feel that, wait, how would you think about this? Another option is to start from each of the two sides. and try to meet somewhere in the middle. Okay, try to get the same on both expressions, then it's the same thing. Okay. Now let's do number D, letter D. This one actually is pretty cool. So if we have Z that is AB, so we have Z that is the absolute value that is the square root of A squared plus B squared. Okay, and because A and B are both of them non-negative, they could be zero, right? But at least we know the squares are non-negative, so we know that the square root of A squared plus B squared is bigger or equal than the square root of A squared alone. Okay, but now we realize, oh, A is a real number, so this is the absolute value of A, but A is the real part of Z, which is what we wanted to show. Okay, that the real part of Z is less or equal than the absolute value. All right, and I think we are only left to prove the triangle inequality. That was E. Let's copy paste. There we go. Because we are starting the proof, let's put a question mark to indicate that we want to prove that. Okay. All right. So again, what I was saying before, because in principle, so let's write Z equal AB to make things easier. Let's start with this. W is CT. What I was saying before is here we have the square root of A squared, well, MS. Okay, so it's AC squared plus B plus D squared, and so on. But we have the square root, and that complicates things for us. So what we would like to do first is to look into Z plus W squared. Okay, this always simplifies your life. And in this case, let's go straight for that property that says that the square of the modulus is the product of the number times the conjugate. Okay. Now, the conjugate of a complex number, of a sum of complex numbers, is the sum of the conjugates, right? And then here we need to expand the product, plus C times conjugate of W, plus W times the conjugate of Z, plus W conjugate. Okay, and notice here what happened. We have these, well, here I'm going to make a claim. And this one I leave for you to prove. Okay, so you check this one. The claim is that this is the real part of, well, actually twice the real part of Z times the conjugate of W. Okay, and now we identify what is this and what is this. These are the modulus of Z squared and the modulus of W squared. So we have Z squared plus twice the real part of Z conjugate of W plus the modulus of W squared. And well, right now things may or may not be looking very good. Depends on if you have seen the next move or not. So here what we are going to apply is the previous property that we shown, right? That the real part of Z in absolute value is less or equal than the modulus. So let's apply that here. Okay. And we have that Z squared plus twice Z times w plus w squared. And here, just to conclude, this is z times. So notice that because it's a product, the absolute value of a product, we can write the product of absolute values. Okay, but then the absolute value of the conjugate is just the absolute value of the number itself. And here we go. This is z plus w in absolute value, both of them squared. And oh, I missed the inequality here. So if someone noticed that, good job. So if we go back, we can see that we have the z plus w in modulus square less or equal than the square of z plus w in modulus, both of them. So then we can remove the squares and we get z plus w less or equal than modulus of z plus modulus of w. And we are done.